What they do, Jade. So obviously this is not meant to go into ridiculous detail about them. I want to plant the seed that they exist and their use, and then incite your curiosity for graduate school, or when you get a job, you could say, "Hey, let me look more into this to see if this can help in my profession or career." So the key things is just overall, what do they do? Electromyography is a way to measure muscles and in certain conditions to see if how much they're working, to see when they turn on, to see code contractions, and there's different ways or different questions you can answer with electromyography to see if muscles are turning on. So this has been a consistent thing for us since 310, right? Muscles turn on to do a job. And so you would expect certain exercises or certain patterns to turn certain muscles on. So what if they aren't turning on? What if there's a problem? What if one of the problems you're having with a client or an athlete or a patient is because maybe muscles that should be turning on aren't turned on? How do you test to see if a muscle's turning on? You're going to take the word for it, right? So electromyography is just a system that we can do uh, to actually quantify if those muscles are turning on, when they're turning on, et cetera. Force plates or fancy scales, right? So force plates are great to measure forces that we get back from the ground in 3 dimensions. So a bathroom scale is this, but a fancy force plate could give you this plus this, and so it can give you friction forces, it can give you ground reaction forces, and then obviously the combination of those three is resultant forces that are at angles. So in other words, if the force plate gives you this, that means some of it is here, some of it is there, and some of it is here, and then you put all that together. Um, so it the really it's to know what they are. If I say on the test, which of the following looks at ground reaction forces, right? Well, that's not electromyography. Or I might say, what does EMG stand for? Electromyography. Very basic questions that if you watch the lectures, you would know. Nothing in detail. And then the one from today with motion capture, mocap, being able to actually, you know, the human eye, you just can't trust it. And I know it's what we have, but if you're trying to work with an athlete to improve their skill, having equipment that you can use to actually quantify where they are at different parts of their motion and timing, and you can compare and contrast, and you can do before and afters, and so motion capture can help athletes. It can help if you're a clinician working with people on proper lifting mechanics and form, being able to kind of map out their movements and put it in the computer and actually measure angles. And you know, it's kind of hard to take out a goniometer and measure an angle of someone while they're doing stuff, right? So mocap can give us all that information. It can measure hip angles and elbow angles and shoulder angles and all the different angles. And so, again, to answer your question, just what are they in terms of very basic nature of these three main types of equipment that we have in biomechanics for research and clinics, man. A lot of clinics use these types of biomechanical tools. Examples of each type of lever. So, Emily, great question. Remember that I am going to emphasize lever questions with purpose. So, yeah, you need to know. Oh, you're welcome, Jade. Thank you for that question. So, yes, you're going to need to know the basic book stuff, right? First, second, thirds, and axis in the middle for the first, and axis on. But at the end of the day, my job is to teach you. So what? And that's why I tried to simplify it, where levers serve functions of simple machines. They give you advantages at trade-off of disadvantages. You can't have the best of both worlds. You can sacrifice for certain things that you need. And so that's going to be the essence of the lever questions. If I say something like, what type of leverage in your body is going to really be advantageous for balance? Right away, you should be like, whoa, first class levers really help with balance. And you could again imagine you balancing on your foot and how your foot would kind of be like a teeter-totter, the axis, and you have muscles on the inverters and the everters kind of balancing you, you know. And if you're on two legs, you have flexors and extensors front and back, and your hip is the axis balancing you, and abductors and adductors, and your hip is the axis balancing you. And if you were going to do an upper extremity equivalency, if you're let's say you're doing a push-up, you need a balance. And so you have muscles on each side of the first class teeter-totter balancing. If you really want to see it, you could balance on one arm, and you could see how you're constantly pulling with muscles in all different directions to help balance you, to keep your center of mass over your base support. So you need to know that first class levers can serve one or more functions of a simple machine: balance, redirect. So with a first class lever, I pull down this way and the other side goes up, redirection of an applied force. Your hamstrings do that when you do a deadlift. You pull down on the pelvis so that your upper body can go up, right? Your hamstrings pull down so that your upper body can go up. That's a function of a first class leverage arrangement. And then based on if the muscles are close to the axis, that's speed; far away from the axis, that's moment. And those concepts are trade-offs. You can't have speed with high moment, and you can't have moment with high speed. That's force velocity inverse proportionality. And a super easy way to see that is with muscles, where if I have no muscle, if I have no weight in my hand, I can flex my arm very fast. But the more load I put, the slower that flexion is going to occur. Not the exact same thing, but very similar, where if you have muscles pulling very close to the axis and there's not a lot of load, you can move it very fast. But the further muscles insert away, that's the greater the distance they have to travel. And anytime you have to travel greater distance, it's going to take more time. The last lecture I did last week, I actually did the little lever, and I explained how if you have a lever, go back and watch that review. And I explained that if you have a lever here, and I did a crisscross analogy like this. And if this is the axis, and I go from point A to point B, point A to point B, look how small that distance is, and look how great that distance is. So if I were to step on point A to B, assuming this lever doesn't break or snap, is going to change its direction. It's going to change its position in the same amount of time as that A to B. So if these 2 points change position in the same time, and these 2 points have to change a greater distance in the same amount of time, then this side has to be going faster. So that's why forces applied close to the axis have the advantage of speed and range of motion on the other end, because small changes in muscle contraction produce large changes in range of motion on the other end. Bicep inserts very close to the elbow, so small changes in contraction distance create huge sweeping changes on the distal end. And then the trade-off: if I'm applying my force over here, if my muscle force is applied on this end, well, this is going to take a long amount of time, and so this is going to occur much slower. Okay, that's the old there's someone trapped in a cave and a boulder is, and you got to create leverage to move the boulder. Well, you ain't gonna move it fast, but it doesn't matter if it goes fast. You just have to move it. So when you're moving heavy loads, second class arrangements favor torque production. Now, one of the things I emphasized in the videos is that all types of leverage can help when you're moving something heavy. Why? Because fast moving levers can still go slow. It's just that slow moving levers can't go fast. And I know that doesn't sound fair. And the analogy I gave last week for the Q&A is that Usain Bolt, the fastest man alive, can choose to jog. He could choose to run as fast as me. I can't choose to run as fast as Usain Bolt. So when you're talking about moving something real fast, slow leverage muscles that insert very far away, stay silent. They don't contribute because they can't contract fast enough to keep up. So, um, an example of that is if you flex your knee as fast as you can, hamstring, sartorius, gracilis, all of those traditional knee flexor muscles can contribute. Gastrocnemius stays silent because at the knee and open chain, it's a second class muscle. It inserts early and then, it crosses early and inserts way down on the heel. It has a super long contraction distance to keep up with those hamstrings that are pulling right near the axis. Okay. If I was doing a hamstring curl with a lot of weight, all of the flexors can help because with heavy loads comes slow speed, and fast pulling leverage muscles can work slowly. It's just that slow leverage muscles can't work fastly. So again, it's function. If I say speed and range of motion, you should think third class muscle arrangements. If I say moment and torque production, you should think all three can contribute, but the second classes are going to contribute more because they have the advantage of torque arm, they have the advantage of moment production. And then keywords like balance, redirect, and applied force. Those are key terms that deal with first class arrangements in the body. So again, we're going to use leverage for what we need it for, whether we need balance, speed, or torque. I hope that helps. And thank you for the question, Emily. If you remember last review or in the lecture that it's unfair, and I explained why, we don't say things like the ankle is the elbow is because there's a lot of different muscles that are influencing him. So we can't say that the elbow is a certain type of lever because that's basing a lever off of an axis. We have to base a lever off of the axis and all the different forces that are trying to influence that axis. So again, you can have a first class lever arrangement at the elbow if the extensors and the flexors are both working together for balance, right? Like holding your arm out. You'd have co-contraction there for balance. That's a first class lever arrangement because you need balance. You need stability for balance. So it depends on what you need it for. We should never say the shoulder is the knee is the ankle is That's not how levers work in the body. Levers in the body work based on what we need them for. Yeah, you can have, like, here's an example. At the shoulder, the biceps is a shunt because it crosses the shoulder early and inserts way far away relative. But at the elbow, it's a spurt because it crosses late and inserts very close. So that's why typically, it's kind of cool. That's why bicep injuries tend to happen up here at the shoulder, like in throwing and stuff, because of its shunt like slowing down eccentrics to slow down the shoulder motion. Um, so yeah, and listen, shunt and spurt is just fancy names for seconds and thirds. Third class functions are going to be speed and range of motion. Spurts, shunt like functions are going to be seconds. And again, that duality, that trade off between the two. And again, it's so cool, man, when you think about speed, force, and power lies somewhere in between, right? Power is forceful speed. We talked about that with human movement patterns. You have muscles that mechanically lie somewhere in the middle. You have some muscles that insert very close to axes. You have other muscles that insert very far away from axes. And then you have some muscles that kind of insert in the middle. Like, say, my deltoid, it's not super close, it's not super far, it's somewhere in the middle. So you could kind of see some of these muscles that kind of have a duality to them, a more powerful type muscle where you don't want to sacrifice too much speed and you don't want to sacrifice too much torque. And so that's another cool way to look at muscle insertions. Powerful muscles are going to kind of have live somewhere in the middle. Is this interesting information for you, exercise science majors? Thank you, Emily. Maybe one day one of you is gonna go to chiropractor school, and you're gonna be able to take care of an old and aging biomechanics professor and help me with my neck stiffness. Anybody want to offer some feedback on this material? Do y'all feel more comfortable with non muscle function material now that we're off of that kind of stuff? How y'all feeling going into the final with the new material? I'm going to ask you guys some questions now. All right, guys, last call because it's kind of awkward just to breathe on camera. Okay. Well, let's first look at the definition of Newton's second law. Can you better classify us why we can only apply Newton's second law unless we compare the two? The two what, Anna? The two what? Well, you're asking me the two what, and I'm asking you the two what. The two what? I'm only clarifying because I need to know exactly what you're asking. I mean, Newton's second law is kind of can take us all over the place. So I want to make sure that I'm taking it where we need to take it for your specific question. So what do you specifically mean by the two what? Like, do you mean like the two sides? Like the left side of Newton's second law, the right side of Newton's second law? Or do you mean the concept of Newton's third law applying to Newton's second law, which is if one object is feeling certain forces from an external force, then that force has to also feel something from the object that we're applying Newton's second law to? In other words, you can't apply Newton's second law to one thing and not have Newton's second law apply to something else at the same time. We can look at them independently, but those things are happening together. Is that what you mean? Again, I just want to make sure that I'm taking it where you need me to take it. So if you could clarify that question, that would help me help you tremendously. And thank you for the question, by the way. Excuse me. Let's see. Okay. Sure. So let's say let's take this Sharpie for example. Okay, this Sharpie is an object. It's something. It has mass. It has stuff. I could apply Newton's second law to it because Newton's second law applies to its singles counseling. Like I say in the lectures, it applies to one object at a time. So I could say, what are all the different forces influencing the Sharpie? Planet Earth is pulling down on the Sharpie, and I have my fingers pushing up on the Sharpie. I don't really have anything going across, right? So the sum of all the different forces acting on the Sharpie is directly proportional to the Sharpie's mass times that Sharpie's acceleration. In this case, the Sharpie is not speeding up or slowing down, right? So the right side of Newton's second law is zero. So that means the left side has to be zero. That means the force in the negative y has to cancel out the force in the positive y. In other words, if you owe somebody $20 and you make $20, then you have $0 because whatever you made, you just gave, right? The transaction sums to zero. Okay. So if I wanted to accelerate the Sharpie, I'd have to have more force pushing up than planet Earth pulling down. And I would have leftover positive force. When I'd sum those forces, I'd have more force in the up than in the down. So the sum of the forces would give me a positive unbalanced force. Therefore, the acceleration of the Sharpie is going to be positive. It's going to speed up going up. Now, the duality is that if this Sharpie feels a positive force from my hand, then that means my hand must feel a negative force from the Sharpie. That's Newton's third law. So I could look at my hand from Newton's second law and say, what are all the different forces feeling on my hand? But Newton's third law is just specifically to these two forces from these two different objects and how they feel each other. Sharpie feels hand pushing up, hand feels Sharpie pushing down. That is that objects have to feel the same from each other and equal and opposite. For every force one object feels, there's an equal in magnitude yet opposite direction counterforce some other object must feel. That is Newton's third law. So the same thing goes with gravity. If the Sharpie feels negative gravity from planet Earth feels a positive pull from this Sharpie 3,000 miles down. It's so insignificant, Earth doesn't really feel it. It's a blip on Earth's radar of other huge objects, but it's there. It has to be there because Newton's third law yields it so. Other examples of it is the moon and the earth, right? They're both pulling on each other. Moon feels earth pull. Guess what? Earth feels moon's pull. And if you're like, I don't believe you, that's how the tides come about, right? The tides are because of the moon and the sun's pull and its effects on objects on earth that aren't nailed to the ground in large quantities. That's what the tide does. You know what else is cool? When the earth is here and the sun is pulling on the movable parts of the earth, the tide here, and the moon is here pulling, and they can cancel each other out. That's actually low tide. So when they're lined up, you have more pull here, you got a bigger tide, and you have here, you got pulling on both ends, you have bigger tide. So actually, when you have low tide, that's when the sun and the moon are perpendicular to each other, and they cancel out, and you get less bulge from the water parts. That's kind of cool. So let me know if that was helpful. And if not, we could follow up with more if you have follow-up questions. I don't mind at all. So, like I said in the lectures, Newton's second law is like singles counseling. You're just looking at one object at a time. And then Newton's third law is how those objects feel each other. Specifically, my foot feels the ground, ground has to feel my foot. And they have to feel each other with the same amount of force. If I'm not touching the ground is not touching me. If I'm barely touching the ground is barely touching me. If I'm forcefully touching the ground is forcefully touching me. That's Newton's third law. That objects must feel each other with the same exact amount of force in opposite directions. And that should be a general recap of physics, but I emphasize how it applies to us. If we need to understand that if we are influencing objects in sport, bats, balls, equipment, that our influence on them is going to have their influence on us, right? When the bat hits the ball's hitting the bat. That's kind of how that works. And sometimes the ball does more work on the bat than the bat does at the ball. And that's when the bat gets knocked out of your hands or the bat breaks. Sometimes the ball does more work on the bat than the bat does work on the ball. It happens. What a great question, Anna. Thank you for asking that question. Oh, all right, guys. Y'all have my cell phone. If y'all need to follow up with anything, let me know. And hope this helped. We'll talk to you later.